And Xinlang Hu will give the talk.
Thanks for the introduction. Hi everyone, I'm Qinliang Hou. This talk is entitled "The Generic Meet-in-the-Middle Attack Frameworks on Smart Construction." It was divided into 5 parts. We first give a brief introduction on hash functions. Hash function can map a message of arbitrary length to a fixed length digest. The security properties are defined to resist the preimage, second preimage, and collision attack. And these properties means that a malicious adversary cannot replace or modify a message without changing its digest. And many information security applications are designed based on secure hash functions like signatures or blockchain. However, at the beginning of 21st century, many famous hash functions like MD5 and SHA-1 are broken successfully. So NIST had to hold the SHA-3 competition, and KKR was selected as the winner. KKR use a sponge for hashing purpose, and the sponge operates on set of BBs with RB's out part and CB's inner part. The RB's outer part determines the rate at which message blocks are observed and digests are extracted. The CBD inner part is an important security parameter for us to build a different attack framework. Then I will give a brief review on meet-in-the-middle attack. Meet-in-the-middle was first introduced by Diffie and Hellman to investigate the security of multiple encryption schemes. The following example can be the code of meet-in-the-middle can be well explained by the following example. Assuming K1 and K2 are independent secret keys. The collision between the encryption with K1 and the decryption with K2 can be used to filter out wrong keys, and then the searching space is reduced. In the last decades, a lot of enhanced techniques are proposed to improve the power of meet-in-the-middle, and it has been widely applied to the cryptanalysis of both ciphers and hash functions. Most previous meet-in-the-middle attack mainly targeted on the so-called macro dumb guard hash constructions, and with a feed-forward mechanism, it forms a closed commutation path. Then the threads and cut attack framework can be deployed to cut the whole computation path into 2 independent chunks at certain internal routes, which is called the initial structure. Out of the initial structure, to neutralize with DR neutral bits colored by red and DB neutral bits colored by blue are selected, which determines the degree of freedom for backward and forward trunk respectively. Then 2 trunks will meet at a certain internal round to pass an ambit partial matching. Step 1, 2, 3 are called one meet-in-the-middle episode. To find an H-bit targets, at least 2 to the H minus DR minus DB episodes should be performed. The overall time cost compared with the brute force, the overall time cost had an advantage of the minimum of DB, DR, and M. So a natural question is, does it still work for smart constructions? For macro dumb guard construction, searching at model 2 to the H internal states are enough to find a H-bit preimage. Well, if we deploy the meet-in-the-middle at some internal states in the middle for smart constructions, not only the HB's target, but also the CB's initial value should be satisfied. So the certain space is 2 to the H plus C. Obviously, it's not so compact. This issue was first settled by the conditional meet-in-the-middle attack proposed by Qin at Eurocrypto 2023. In their model, the attack starts as the outer part M2, and the inner part is viewed as constant with some conditions. This condition is determined by M1. So these conditions can reduce the diffusion of two neutral bits, and we do not consider take the state base initial value into account anymore. And the calculation of time cost is same as stated above, except for an extra cost to find a proper M1 satisfying all bit conditions. But Qin's model doesn't always succeed. At Eurocrypto 2022, the general preimage bound was proved to be such formula, and if 2 to the H is not the general bound and exceeds the general bound, Qin's model may do not work. We take the Symmetric as an example. According to the above formula, 2 to the C over 2 is the general bound, that is 2 to the 128. For Qin's model, at least one meet-in-the-middle episode should be performed, and the optimal time is achieved when dr, dB, and m are equal to the H over 2. That is also the 2 to the 128. That means Qin's model has no threat to Symmetric, even if the time cost is achieved at the best. So we are motivated to find out a more general attack framework on Swan constructions. The attack framework in our paper consists of two phases. In phase 1, we start at the capacity at the first screening phase, and we use the Qin's model to find a capacity X satisfying the remaining H minus R prime digit base, and once such an X is found, we need to find an inner condition at an internal state Y. This is done to keep the consistence between T1 X and the initial value. To further reduce the time cost, we could fix some base, partial base of Y to be constants. Then we could only find 2 to the same minus T over 2 messages, and for the forward meet in the middle, and this is same for the backward meet in the middle. And once we found such messages, we could find a collision at C minus T base. According the general bounds as stated above, there is a huge difference in time between phase 1 and phase 2. So we consider the three cases. For the case 1, if H minus R prime is less than C over 2 and less than H, the general bound is 2 to the C over 2, according to the formula. Therefore, phase 2 dominates the overall time cost. We only consider the phase 2. And for the X in phase 1, we could fix it at a constant. The typical example is the Sphinx Harlock. For the second case, if H minus R prime equals to the CO2, the general bond are to the H minus R prime and to the CO2. So phase 1 and phase 2 are both needed. And typical examples are Gemini and Zodiac. For the last case, if H minus R prime is greater than the CO2, the general bond is 2 to the H minus R prime. So phase 1 dominates the total time course. And the inner creation in phase 2 can be performed trivially in time of 2 to the CO2. And the typical example are Ascan hash. We take the Sphinx Harlock as an example. Sphinx Harlock is a sponge-based hashing based on the 512 bits permutation of Harlock volume 2. The internal state is a concatenation of 4 AES states. In each round, 2 AES rounds are applied individually on each AES state, followed by a column-wise mix operation. Our target is 4-round Sphinx Harlock without the last mix operation. For the forward mid in the middle, 16 bytes in MC7 are fixed to be 0 as the matching points, and the starting state is MC1. There are 12 blue cells and 12 red cells. With time of 2 to the 96, we could find 2 to the 64 M2, satisfying the 16 bytes 0 bytes. And we store them in a hashing table L1 indexed by the undetermined bytes of our inner part in MC7. For the backward, it's similar. We also fix the 16 bytes in A0 to be 0 as the matching points, and with time of 2 to the 96, we could find 2 to the 64 M4, satisfying the 16 0 bytes. And we store them in L2 and indexed by the undetermined bytes of outer part in A0. At last, we could find a collision between L1 and L2. For the inner part in A0 and MC7, this can be easily modified by a free message MC3. For the collision attack, we also improve Chin's model to be more general. We provide 2 collision framework. For the first collision framework 1, the attack procedure aims to find 2 messages leading to the same HB's targets directly. Well, for the second one, it aims to find a collision at some internal states. Similarly, according to the general bound of swan correction, for different parameters, we consider the 3 cases. Since the first framework had been discussed in Chin's model, so we give a typical example. We give an example for the second framework. That is a collision attack on 3-round Ascan hash. Ascan is a winner of the NIST lightweight cryptography project. For the nonlinear operation, it's a 5 bits column-wise S box, and the linear layer is diffused. In the linear layer, each row is diffused with some predefined linear functions. Since for the parameters of Ascon hash, we can see that h equals c. As said above, when h equals to c, collision framework 1 or 2 are both okay. But we will show that collision framework 2 will be much better. That is the S-box of Ascon hash. We give the opposition one. Is a matching strategy for collision framework 2. Since collision framework 2 allow us to set to fix bits to be constants at the inner part, and we will observe that if the last four bits of the output of S-box to be 0, then we can obtain 4 matching equations immediately. Using these properties, we can set the last four bits in these columns to be 0. We can get more matching equations than the collision framework 1. The configurations are there are 24 DR and DB red bits, and the matching points is also 24. So the total time cost is 2 to the 113. Okay, at the last, we give a summary of our results in our paper. Compared with the previous better results, the collision attack on Ascon hash is improved by 2 rounds, and we also improved the pre-imaging attack. We also improved the Sphinx Halak 3.5 quantum pre-imaging attack, 2 hours, 4 rounds classical pre-imaging attack. Besides, we also give some the first third-party cryptanalysis results on some widely standardized hash functions like Photon, SH. Okay, that's all for this talk. Thank you.
Thank you very much. Any questions for our speaker? So did you try to apply your techniques to SHA-3 to Keccak?
For SHA-3 and Keccak, okay. For SHA-3, the parameters h equal to the c over 2. So the general bound according to the such formula is 2 to the h. So there is no new results on Keccak and SHA-3, and it's that's the same as results at Eurocorp 2023 by Chin's model.
Okay. Well, this time speaker again. Thank you very much. So we move to the second talk of this session, entitled Improving Generic Attacks Using Exceptional Functions, joint work between Xavier Bonnetin, Rachel M. Boissier, Gaëtan Laurent, and André Schottenlohr, and the exceptional Gaëtan Laurent will give the talk.
Thank you for the introduction. So this is a talk, we are in the symmetric cryptanalysis session, and usually when we do cryptanalysis in symmetric crypto, it means we're looking at primitives, because that's the only way we can evaluate them using cryptanalysis. So that's typically what we do with cryptanalysis. And so what we do so we start with primitives, we do cryptanalysis, and then we put them in modes of operation or generic construction. And those objects, we study them usually with security proofs, starting from the assumption that the primitive is good. But in this talk, I will do something different. I want to apply cryptanalysis on modes of operation and generic constructions, because it also gives us more information. So we will look at generic attacks, assuming that the primitive is good, and looking outside the primitive, what can we do on the mode, what can we do on the generic construction? And this is interesting because if you only do proof of security, you get lower bounds on the security. But if you also look at those generic attacks, you get an upper bound. And sometimes there's a gap, and it means it's interesting to look more into what's happening, and sometimes it's tight, and then you have good confidence that your proof is optimal. And typically what happens with the construction we use in symmetric crypto is that they reach birthday bound security, meaning that we have a proof as long as the attacker performs less than 2 to the n over 2 operations, where n is the state size. And sometimes we have a matching proof, but sometimes we don't. In particular, for more complex constructions or more complex security notions, we don't always have a matching attack, and that's where it's interesting to look at this type of generic cryptanalysis. So to give a simple example of generic attacks, maybe the easiest one is Pollard row. So it's a very simple attack. You are given a public n-bit function, a hash function, and you try to find a collision. And the way this works is you start with some arbitrary initial state, and you're going to iterate your function h. So you build a sequence, xi is h of xi minus 1. And at some point, this sequence will cycle because the domain is finite. And if you look at the graph, it looks like a row, and that's why it's called Pollard row. So that's basically the algorithm. And if you want to analyze it, to understand its complexity, you have to look at properties of random function. What we do is we assume that h will behave like a random function. We'll have the average property of a random function. And under this hypothesis, we know that the time to reach the cycle, so from the starting point to the cycle, there are about 2 to the n over 2 steps. And the size of the cycle is also about 2 to the n over 2 steps. So the total complexity is about 2 to the n over 2. And this is assuming average properties of the function h. And this is a reasonable assumption because if h is very far from random, then you have other issues than generic attacks. And in fact, the properties of random function have been very widely studied, in particular by mathematicians. And what we usually do is we look at the graph. So that's the same idea as in Pollard row. We consider the function as a graph between an edge between the input and output. And we know that there are cycles in this graph, several of them, and there are trees connected to the cycle. And we know lots of properties if we, on average, over all the random function. We know the number of components, cyclic nodes, tail length, cycle length, the size of the largest tree, the size of the larger component. And this is very interesting for cryptanalysis. Many of those properties have been used. And in particular, something that's a little bit surprising is that there is a giant tree in a random function. So this would be this one here. And on average, you expect that the largest tree has size almost half of the full space. So if you start from a random point, there's a very high probability to be in this one specific tree. And this means in terms of cryptanalysis, if you have a construction that iterates a fixed public function, you can do some pre-computation to identify this giant tree and the root of the tree. And then you know that starting from a random or secret point, if you iterate, you are likely to enter the cycle at one very specific point. And this point, you can compute it offline because the function is public. And this was used, for instance, in attacks against HMAC. And this is all assuming average property of random functions. But there are also things that are known about the distribution of those properties and how they can deviate from the average. And in particular, something that happens with some probability is that the giant tree can be connected to a small cycle. So on average, you expect that the giant tree is connected to the largest cycle of size about 2 to the n over 2. But sometimes it will be connected to a small cycle. And when this happens, this creates a large component because you have the giant tree in it, a large component, but with a relatively small cycle. And this is interesting in terms of cryptanalysis because now if you have this, you know that starting from a random point, if you iterate long enough, you will likely reach this small cycle. And so this strongly reduces the entropy of the state. And how can you use this? Well, it's useful if you have not a single public function, but a family of functions with some parameter. and if the parameter is chosen by the adversary. And in this case, what the adversary can do is try many different parameters, measure the size of the cycle in the main component, and select a specific parameter so that the main cycle is small. And this was proposed by Gilbert, Haimboissier, Cathy, and Rotella at Eurocrypt last year. And they show that the complexity to find a good parameter is about 2 to the n minus mu, where mu is the length of the cycle that you're looking for. And they use this for cryptanalysis. In particular, they've been looking at the duplex sponge, which is a very popular construction to build authenticated encryption. So we've seen Ketchak in the previous talk. This is the same idea, but now you're not doing just a hash function, you're doing authenticated encryption. And so you start from a public permutation, you initialize the state with a key, and then block by block, you XOR your message in the state and you extract the ciphertext. So that's when you do encryption. When you do decryption, you have to reverse the encryption, of course, so that it works. And in particular, this means that the ciphertext will replace part of the internal state. And that's interesting because if you look only at the tag verification, what happens is you are iterating this construction with a public permutation and with some ciphertext block that can be chosen by the adversary and that replaces part of the state. So this is exactly the setting of earlier. We are iterating a function that can be chosen by the adversary. And so if the adversary fixes the ciphertext block to some constant value beta and uses a very long message with lots of blocks of beta, with high probability, the state at the end will be in the main cycle of this function here, h beta, which is built from the permutation and with the constant beta. And this gives a forgery attack, which is actually relatively simple. When you put everything together, the idea is you start by choosing some value beta, you look at the function h beta, you search its cycle, and you're going to pick some point in the cycle, x star, and from this point you can compute the finalization and compute a tag, assuming that the final value is this fixed x star. And next, what you do is you take a message with a very long message with all the blocks fixed to beta, and you're going to assume, to guess that the final state is exactly this x star, and therefore you know the tag, and this gives you a forgery attempt. And in terms of complexity, if you do this by just picking an arbitrary beta, then you expect that the cycle at the end has length about 2 to the n over 2. So the probability of your attack, the probability of success is about 2 to the minus n over 2. So you have to repeat 2 to the n over 2 times, and you use a message of length 2 to the n over 2 so that you reach the cycle and you end up with complexity 2 to the n. So that's not very interesting. But what they showed in the Eurocrypt paper last year is that if you start by finding a particular beta that leads to a small cycle in the main component, then you get a better attack. There's a pre-computation cost to find this good beta, but then the forgery attempt is more likely to succeed because you have a smaller cycle. When you balance the parameters, you obtain an attack with complexity 2 to the 3n over 4. And that was the first attack with complexity below 2 to the n for this specific problem. So that's basically the state of the art about using exceptional functions. And what we do in this new paper is we try to extend those results and to apply them more generally. And we have two contributions. The first one is a new technique where we use a nesting construction for exceptional functions. And the second one is that we revisit several attacks in the literature, and we show that several of them can be improved with this technique of exceptional functions. So let's start with the nesting construction. So the idea is actually relatively simple. What we do is we start with some function h beta. We look at the graph of the function. We know there is a cycle, and with high probability, when you use long messages with lots of beta, we end in this cycle. And the idea is we're going to build a new function that operates inside this cycle. So a function that starts from the cycle and ends in the cycle. And the idea is that this function operates in a small domain. So at some point, it will also reach a cycle, but this second order cycle would be much smaller than the first one. And how do we build this function? Well, we use this construction here. It's actually quite simple. We first apply h with a different parameter, so not the beta that we use to build this graph. And when we do this, it means that we do a move that does not follow the graph. So we move somewhere randomly. And then we apply a long sequence of h beta. And with good probability, this long sequence of h beta will send us inside the cycle of the main component. And so to show you a concrete example, if you start from x0, you move somewhere with beta, and then you use this long sequence, sorry, this is with gamma, and then you have a long sequence of beta, and you reach the cycle. So if you look at the new g function, it will go from x0 to x4. And then we can iterate. If we apply it from x4, maybe we go to x2, then from x2 to x1, and then maybe from x1 to x1. And this means we have found a cycle in G, and the cycle, of course, is much smaller than the first cycle. So what can we do with this? Well, we can directly use it for a forgery attack on the duplex sponge. And the idea is we're going to use a ciphertext that corresponds to this nesting construction. And what does it look like? Well, we have blocks like this with one message gamma, then a long sequence on beta, and we repeat those blocks many times. And the idea is the long sequence of beta will send us to a cycle C with high probability. And by repeating those blocks many times, since each block corresponds to a function G, with good probability at the end, we end up in the cycle of G. And so the attack is very similar to the previous one, only we use a different message. And the precomputation is slightly different because first we have to find a good beta such that H beta has a small cycle of length 2 to the mu. Then we find a good gamma so that the function G beta gamma has a small cycle of length 2 to the nu. Then we take some point in the small cycle, we guess the corresponding tag, and then we can make a forgery attempt with this message here. And when you look at the complexity, you have to balance all the parameters to find the optimal complexity, and you end up with 2 to the 5n/7, so that's better than 3n/4 that we had before. So that's already an improvement, and in fact, we can also do even better, but by adding a step, a precomputation step here, after finding beta and before finding gamma, we can do some precomputation based on beta. We can actually compute a big part of the graph of H beta. And the idea is if we compute many elements in this graph, afterwards, when we compute long chains of beta, we can reuse this computation to speed up the computation of the chain. So we start from some given point, we iterate with blocks of beta, and as long as you reach the pre-computated part, we can just directly get to the end of the sequence. So this improves the second part of the pre-computation. And again, there are many parameters. You have to balance everything, and you end up with complexity 2 to the 2n/3. So that's significantly better than before. But of course, there's still a gap with the security proof, which is up to the birthday bound. So we still don't know what is the exact security against this type of attack. Another interesting property is that when you balance the parameters, you end up with nu equals to 0. Which means that the function G that we're building, instead of having a small cycle, it actually ends with a fixed point in the main component. So the giant tree is connected to a fixed point. And that's actually a relatively strong result. And this gives something that could be a new tool in the toolbox for generic cryptanalysis. We have this property that if we are given a family of functions with some attacker-chosen parameter, we know how to build a specific sequence of parameters of length 2 to the 2n/3, such that at the end, the point that we reach is a fixed known value with high probability independently of the state at the beginning. So starting from any secret state, we can guess with high probability the state after processing all this sequence of functions. And this could be a useful tool to attack a variety of targets. We show that it can be used on HMAC, the zipper hash, or a hash twice. But unfortunately, this attack has complexity 2 to the 2n/3. And for those constructions, there are already better attacks known. So it doesn't improve the state of the art, but it's like an alternative attack. And maybe this tool can be used in other places to improve the state of the art. So I now move to the last section. We're going to look at various attacks in the literature that are based on average properties of random function, and we show that some of them can be used using exceptional properties. And in particular, we look at hash combiners like the XOR combiner, the zipper combiner, or hash twice. So let's start with the XOR combiner. So what is this construction? It's a construction where you start with two different hash functions, h1, h2. You give them the same message as input, and you XOR the output. And the idea is that this would be more robust than just using a single hash function. Like maybe if you XOR SHA-1 and MD5, you get something that's not completely broken. That's like the intuition behind this construction. And in terms of cryptanalysis, what we have to break looks like this. So we assume both functions are Merkle-Damgard. So you iterate a compression function, and on both sides, you have to use the same message block, and at the end, you XOR the two results. And what's interesting is that in 2015, it was shown that we can do a pre-image attack on this construction better than 2 to the n. And the idea of this strategy is to first build a structure so that we can control the two hash functions independently. And without going into the details, what we want, what I call a structure, is a set of messages and a set of ending points A and B for the functions h1 and h2, such that if you pick a specific A and a specific B, you can directly know in your structure which message to use to reach this specific pair of output states. And this gives you this independence between them, because you can pick independently in A and in B, and you directly know which message to pick. And if you manage to build this structure, then you can do a pre-image attack relatively easily. You just start from your sets A and B, you append a random block W, you compute the new states, and you see if they match with the target value. And if there is a match, then you can directly compute your pre-image. If there is no match, you repeat with a new random block. And if you do the analysis, the gain that you get compared to brute force is essentially the size of A and B. So the hard part is, how do you build this specific structure, this set of message with this property? And there's been several structures that have been proposed over the years. The first one was the interchange structure. Then there was an attack based on deep iterates, and a new one based on multi-cycles. And in this presentation, I will talk about the multi-cycle technique, and I will show that we can improve it using exceptional random functions. So the main idea in the multi-cycle technique is that we're going to iterate long messages with a fixed message block. So it's very similar to what we've seen earlier. And when we iterate, when we build such a long message with the same message block repeated, and we process them, what happens, of course, is that we're going to iterate a fixed random looking function. And the way we build the structure is actually very simple. We start from the IV, we iterate the function, and we know at some point we reach a cycle. This is true in H1, and this is also true in H2. And what we're going to do is just use the points in the cycle as the ending point in our structure, the set A and the set B. And in fact, if we pick the indices correctly, what happens is when you process lambda blocks of beta, you will end up in a state that is exactly A index lambda modulo the length of the cycle. And then the other function, it will be B modulo lambda, sorry, B index lambda modulo the length of the cycle. That's just by constructing this very simple structure. And when you do that, in fact, if you want to reach a specific pair of value in A and in B, you end up with just a simple system of modular equation. You just want lambda modulo the length of the first cycle to be something, and lambda modulo the length of the other cycle to be something else. And we know how to solve those equations. We just have to use the Chinese remainder theorem, and we get a specific value of lambda, which means we get a specific message with lambda blocks of this fixed value beta that will reach exactly this pair of states. So that's the construction, in a nutshell, the multi-cycle attack. And so if we use it for a pre-image attack on the XOR combiner, it gets a little bit more complex than that, because usually when you solve your system with a Chinese remainder theorem, you will get lambda that is very large. And so you get a message of size essentially 2 to the n, and that's not very useful. So you have to repeat a few times until you get lucky and you get a small message. I will not go through the details, but if you do the security analysis, you see that if you start with an arbitrary beta, which was the previous state of the art, you end up with an attack with complexity 2 to the 3n/4. But if you spend some time to optimize the choice of beta such that the main cycle are smaller than expected, so using this exceptional function property, then you end up with a better trade-off, and the complexity goes down to 2 to the 7n/10, which is slightly smaller. So this shows that the use of exceptional function improves this multi-cycle property. I will not explain the full attack in detail because the full attacks are extremely complex and they combine many different techniques. But in a nutshell, we get new attacks that are better than the state of the art for the XOR combiner, also for the zipper hash and for the hash twice. You can see the improvement is not huge, but it is an improvement. And we're going closer to the lower bound of the security proof, but it's still an open question whether we can go down to 2n/2 or whether there is a better proof maybe that meets somewhere in the middle. Thank you.
Thank you very much. I'm afraid there is no time for questions, but you can talk to Gaetan after the session.
You can see me offline.
Okay. So the next talk, and it's not the last talk before lunch, it's the one with last talk before lunch, but it does speak about lunch, the algebraic free lunch, efficient Grosvenor basis attacks against arithmetization-oriented primitives, joint work between Augustin Barriant, Aurélien Boeuf, Axel Lemoine, Irate Manterola Ayala, Morten Overgaarden, Léon Perrin, and Hovard Radum. And Aurélien will give the talk.
Thank you for the introduction. So in this cryptanalysis paper, we looked at these three families of primitives. So Anemoy and Griffin, which were presented at Crypto last year, and Arion hash. So in this paper, we provide a front break of some instances of Griffin, likewise for Arion. And as for Anemoy, well, it's a little more complicated, and we'll see why. Now, in a nutshell, why we have these results is we provide three improvements in previous algebraic cryptanalysis. First of all, we have this technique, basically, that allows us to get free Grosvenor bases for the models of these primitives. And since computing Grosvenor bases is generically pretty hard, this is actually a huge improvement. But that's not all. We also provide a more like dedicated solving algorithm than just generic FGLM. And also, I will not talk about this in the presentation, but we have some symmetric techniques to bypass some rounds in Griffin and Arion. So first, I'm going to give a reminder on what arithmetization-oriented primitives are and the state of the art on cryptanalysis. Then I will talk about what we call free lunch systems, which is basically how we get free Grosvenor bases on to attack these primitives. And lastly, I will describe the solving algorithm. Now, arithmetization-oriented primitives, if you're not really familiar with those, basically recently there has been a lot of advances on advanced protocols such as zero-knowledge proofs, MPC, and FHE. But in the context of these advanced protocols, if you just use AES or SHA-3, it turns out you have a pretty terrible performance. And so there has been this demand of primitives that are more efficient for these protocols. And specifically, it turns out that what that means is that you want like hash functions, for example, that are defined with simple algebraic operations, for some definition of simple that actually depends on the protocol. But so yeah, you have this change of paradigm. So first you have the like classically you have operations that are binary, efficient on a computer. And from the point of view of algebraic cryptanalysis, you don't see a lot of algebraic cryptanalysis necessarily if to cryptanalyze classic ciphers, because you can get pretty algebraically complex operations like for cheap, like the S box of the AES, for example. And usually they're defined over small fields, so F2 to the 8, which is like bytes. But now, for the sake of these advanced protocols, we have to define primitives that have just arithmetic operations that need to be by design algebraically simple. And it turns out that in the end, that means that algebraic cryptanalysis ends up being the most potent kind of cryptanalysis against these primitives. And also, most of the time, they are defined over very large fields. So typically FQ, where Q is greater than 2 to the 64, but in fact, it can even go up to 2 to the 256. And so that means that you have fewer branches, and this is a really different structure than classically. So examples are Griffin and Anemoy. So specifically, we looked at these three families of primitives, Anemoy, Griffin, and Arion. So they are arithmetization-oriented families of sponge hash functions that are instantiated from Griffin pi, Arion pi, and Anemoy families of public permutations, right? And something that I have to mention is that one feature of these designs is that they have many instances. So the base prime field is a variable. The number of branches is a variable, so as in like a parameter. And even the exponents for the nonlinear operations are parameters. And so, for each of these parameters, they have a way of saying, we need this many rounds so that the primitive is secure. But for us, that ends up meaning that some instances we attack much better than others. Just something to keep in mind. Now, to evaluate the security of sponge hash functions, we usually look at the hardness of the Kiko problem on the inner permutation. So the Kiko problem, constraint input, constraint output, is basically you want to get an input-output pair such that the last coordinates of the input and of the output are equal to 0. So generically, you will need to do brute force, and that will require size of the capacity, basically. But for multivariate attacks, what this means is that we define polynomial systems, so preferably of low degree, whose solutions are solutions to the Kiko problem. And so if you can solve the polynomial system, you get solutions to this problem. And in fact, if you can solve the Kiko problem of our size, the capacity, you actually generically get collisions to the hash function, so you break the hash function. And I have to mention that in this paper, we focus on a specific case where C is equal to 1, so just have a capacity of 1 element. So this might not seem like a lot, but again, because the base prime fields are so huge, you actually do have instances that are, defined for like capacity equals 1. So this is actually a case of interest. And now let's look at an actual example. This is the round function of Griffin, basically. And this is kind of a typical round function for optimization-oriented primitives. So the idea is when you look at the nonlinear layer, you have these operations. So this is like x to the alpha, where alpha is a very small integer, like 3, 5, or 7. And then you have these Q2 and Q3, which are quadratic functions. So the idea is you just have only low degree operations, except for this S box, which is going to be our focus, which is x to the 1 over alpha, is the functional inverse of this. And so it has a very high degree, which is what designers want to introduce like resistance to algebraic attacks, but it has a very low degree inverse, right? And so the idea is that because it has a low degree inverse, this doesn't hurt complexity for the zero knowledge protocol because they are defined using systems of equations. But that also means that from the point of view of cryptanalysis, okay. We also have efficient approaches when you do multivariate systems, right? Because the idea, and this is going to be the modeling strategy, for each of these, you're just going to define one new equation and one new variable that's like, output to the alpha equals the input, right? And ideally, this gives you equations of low degree, and maybe you can solve it. Now, the full model is this. In the case of Griffin, so we want to solve the Kiko problem on one coordinate. So you introduce one variable in the input, x0, and you have a corresponding equation and the output that says, I just want the last branch to be equal to 0. And additionally, for each round, you add one new equation that corresponds to the x to the 1 over alpha S box. That's like xi to the alpha equals a polynomial in the previous variables. So you end up with n rounds plus 1 equations and variables. So here's an example. For alpha equals 3 and 1 round, you have two equations. Okay, one equation that corresponds to the first and only x to the 1 over alpha S box. And also one equation which corresponds to, I want the last branch to be equal to 0 on the output. So this is an example of the system we want to solve. Now, generically, this is what you do. First, you define the system, like we just did. Then you find a grammar basis for the system. So for example, using F4 or F5 generic algorithms. Then once you have a grammar basis, you will typically change its order to lexicographical order. So why do you do this? Because you know for a fact that if your system is not underdetermined and you have a grammar basis in lex order, you know that one of the polynomials is going to be univariate. And this is a really nice thing to have because we know how to find the roots of univariate polynomials in finite fields very efficiently. And this is the full algorithm. So among these steps, finding a grammar basis and changing its order are both the most costly steps. compared to the others. But specifically, in the case of Anima and Griffin, the security is based on the hardness of step 2. So finding a Grobner basis. This determines the number of rounds, basically. And in this paper, we provide a way to basically skip this step because we said that we actually already have a Grobner basis. And this is what we call the free-lunch systems. Now, I don't have the time in this presentation to introduce Grobner basis, unfortunately. So, if you don't know what a Grobner basis is, you will unfortunately have to sleep until the next section. But we heavily use this very useful proposition that you might not be aware of, that if you have a system of polynomials such that for a monomial order, the leading monomials are pairwise co-prime. So for example, you just have x and y, x squared and y, then you already know that you have a Grobner basis, just immediately. So here's a few examples. Consider the system x squared minus 1 and a y squared minus x. So if you consider a Graveleg's order, so you first look at the degree of each monomial, then the leading monomials are x squared and y squared. And because they are coprime, this is a Grobner basis. However, if you look at lexicographical order with x greater than y, then suddenly the leading monomials are x squared and x. And so we cannot apply our proposition. And in fact, it is not a Grobner basis. So, the proposition is not an equivalent condition, but yeah. Now let's look at another example. Y cubed plus x and y cubed plus x squared. Now, for any of the usual orders, so lex, deglex, gravelex, this is not a Grobner basis. And so you would normally have to use F4 or F5 to transform this into a Grobner basis, basically. But you can notice that you can use basically a weighted degree order, which is like a more exotic kind of order compared to what you see in the literature, at least for these cryptanalysis papers. And what you say is, I'm going to give a higher weight to x so that the leading monomials become y cubed and x squared. So for example, you could choose x has weight 2 and y has weight 1. And then you do end up with leading monomials y cubed and x squared. And because of the useful proposition, this is a Grobner basis. Now, this example encapsulates everything that we do when it comes to the free-lunch systems. It's basically exactly what we do. We just choose the weights so that we have the leading monomials that we want, and they are coprime. Here's an example. So this is Griffin for 2 rounds now. So you have 2 equations that are like x1 cube equals something, x2 cube equals something, and then the last equation, which is x0 to the something equals 0. Now, the idea is if you use like Revlex, for example, then the leading monomials are going to be x1 cube, and then something in x0 and something in x0. So you cannot apply the proposition, right? But now we say, well, let's give a push to x2 by giving it a higher weight. Now we have that the leading monomers are x1 cube, x2 cube, and x0 to the 49. And since they are co-prime, it's a Grobner basis. And of course, this approach generalizes to any number of rounds. So you can always make it so that the leading monomers are x1, something in x1, something in x2, something in x3, and then something in x0 at the end. And so it's a Grobner basis. Now, this is not the end of the cryptanalysis. You still have to solve the system. And in fact, we have a couple of interesting things to say about that. So generically, you would just use FGLM. FGLM says if you have a Grobner basis for some order, then you can compute a Grobner basis in any other order in n number of variables times di cube. So di is called the degree of the ideal. It's a very, very important quantity when it comes to evaluating the complexity of these solving algorithms. It's basically the number of solutions in the algebraic closure. In our case, it's the product of the degrees of each leading monomial in the system, in our case. Now, why do we look at order change? It's because, again, we know for a fact that in Lex order, you must have at least one univariate polynomial if the system is not underdetermined. And again, we love univariate polynomials because we know how to find the roots. And once you have the roots, you can find out the values of one variable and then just deduce the solutions of the cycle problem, get collisions, blah, blah, blah. Now, I'm going to describe a more dedicated solving algorithm, but the issue is that we do not have tight complexity estimates for this. We do have experimental results, but it's not really completely satisfactory. So before you call me a fraud, let me just say that just using FGLM along with the free Grobner basis free-lunch systems, and also some techniques to bypass some rounds, is already enough to break some instances of Griffin and Ariel. So this is just to go even further beyond. So the idea comes from a paper from 2022, which basically says instead of doing FGLM, let's consider the linear operation that maps any polynomial to x times p for one of the variables x reduced in G. So this is a linear operation, and so it has a characteristic polynomial. And because of Cayley-Hamilton, you basically end up finding that the characteristic polynomial is a vanishing polynomial of x. So basically a univariate polynomial in x, which is, again, exactly what we want. And this is going good. So in the paper, the complexities are generically better than FGLM. The issue is that our systems do not verify a very important property of this paper. So we have to kind of do it by hand. So here's the full, the way we compute the characteristic polynomial. So first we compute the matrix of the linear operation x maps to p maps to x0 times p reduced. And unfortunately, this step, we do not have very tight, we only have very loose complexity bounds for it. So what that means is that this can be very costly or not. Again, we only have experimental results based our analysis on, but I mean, more details in the paper. And then once you have the matrix, you can compute its characteristic polynomial using fast linear algebra. And in fact, it turns out that the matrix has a very specific shape. And so you can actually do a block matrix stuff to reduce this to computing the determinant of a much smaller polynomial matrix of size d1 times dn, basically cutting the d0, which is the degree of x0 in the polynomial system. And since d0 is a much, much higher quantity than all of the other ones, this actually speeds up computations by a lot. This is basically why we are interested in this algorithm, despite the step one that we can't really evaluate the complexity of. So here's the full algorithm. Compute the system and the weight so that it's a free Gromner basis. Compute the multiplication matrix of multiplication by the smallest variable. This has a hard complexity to evaluate. Compute the characteristic polynomial of t, and then just find the roots of key with efficient algorithms. Now, to conclude, we showed that, I mean, basically, these arithmetization-oriented hash functions and similar designs in the future should not base their security on the hardness of finding Gromner basis, as I think we've shown. And instead, we encourage designers to really focus on the growth of this quantity di, which is the degree of the ideal, because all of the solving algorithms depend on this in one way or another, in a way that's very tight. So focusing on making sure that this quantity is large enough is a much better security argument in the light of these results. And also, Adema, Griffin, and Arian, because we have these attacks, they need to recompute the number of rounds in order to be secure. And as far as ongoing work goes, of course, we are very interested in better approaches for MatGen. In fact, we already have some results that we are compiling in the paper, so stay tuned if you are interested. And also, questions are like, are there other contexts where Gromner basis computation is hard and you can actually find these free or cheap Gromner bases using similar methods? Because this can be very, very interesting. And also, we are focused on one branch, Kiko. Turns out that we can't really directly do more than one branch in our model, but there are probably ways of doing it. And yeah, this is an ongoing work, basically. So thank you for your attention.
Thank you. Any questions for Aurélien? So what do you recommend to designers, to increase the number of rounds or make a completely new design, fix their design?
So in this case, increasing the number of rounds will be enough because the complexity of solving algorithms is already pretty high. Like even if it, even with our strategies, it doesn't hit the security bound. Actually, you can get there just by increasing the number of rounds. So, but for sure, there are probably some better designing techniques that can provide specifically protection against solving algorithms, the complexity of solving algorithms. So yeah, we think that there is some room to design better primitives, but yeah, the new number of rounds could be enough.
Okay, let's thank the speaker again. So standing between you and lunch, the last talk of this session is entitled Time Memory Trade-offs Sounded Death Knell for GPRS and GSM. Joint work between Tristan Claverie, Gildas Avoine, Yann Leblanc-Albarel, and Xavier Carpent, and Tristan will give the talk.
So thank you very much. So thanks for the introduction. So I work for the French National Cybersecurity Agency, and this is a collaboration with academia on the security of 2G encryption functions when faced with time memory trade-offs. So in this presentation, we'll define functions that allow us to attack both GSM and GPRS technologies using time memory trade-offs. This is a black box analysis, so it applies in fact to all 2G ciphers. And this allows for practical passive-only attacks against A53 and GA3 encryption algorithms using only 128 bits of non-plain text. And we've not computed the entire table, but we've performed extensive validations of the various hypotheses and how everything works. So first, we're talking here about second generation mobile networks, so 2G in short. 2G is in fact the combination of two technologies. First, we have GSM. GSM is used to send calls and SMSs, and GPRS is used to send IP packets. And you may think that, yeah, but it's 2G, it's not being used. Well, in fact, if you're in a country, you have no coverage of 3G, 4G, or 5G, you will end up using 2G without even knowing. And more concerning, there are a number of connected devices that only have a 2G interface. They're not compatible with anything else. And sometimes they're installed into water systems or electrical grids. And so their security still matters. I'm not going to draw what's a 2G network like, but just imagine that you have mobiles on one hand, you have a set of antennas, the base stations in the middle, and you have a core network. So mobile talk to base stations wirelessly, and base stations talk to the core network with wired protocol. Now, GSM encryption, it happens between the mobile and the base station. And GPRS encryption happens between the mobile and the SGSN serving GPRS support node, which is a specific element inside the core network. GSM encryption uses the A5 family of functions, and GPRS encryption using the GEA family of functions. And we are working here in a passive attacker model, meaning we are here, we have an antenna, we try to look at what's happening over the radio, and we're trying to decrypt the messages. Well, there are lots of 2G encryption algorithms that have been defined, and some of them broken over the years. I've not included the entire literature, but basically for GSM, A51 and A52 were rather quickly broken. A51 has been broken using time memory trade-offs in 2011, and the tables have been published by SR Labs. And GA1 and GA2 have been broken much more recently in a paper at Eurocrypt in 2021. If we look at the other algorithms, A53, A54, GA3, GA4, they all rely on the same underlying block cipher that is called Kasumi. There is a really brutal attack on Kasumi that relies on related key entries and ciphertext, but it's only theoretical in the context of 2G networks, because this attack cannot happen in 2G networks because we don't have those related keys and those amount of chosen ciphertext. So in our study, we're interested in, can we actually use time memory trade-offs beyond just the case of A51, and what is the impact of that? So quick introduction to time memory trade-offs. Basically, the use of the time memory trade-off is to invert a one-way function, imagine you have a function h that takes an x and produces a y. And from this function and a y, you want to find the preimage. You want to find x. Now, the main use case of this is for hash password. So from a hash of a password, can you recover the password? And a time-memory trade-off works in two distinct steps. First, you have a very computation-heavy step that you are computing the hash function over all possible inputs x, and then you store that in an optimized data structure, a table, and the attack step is you just get a hash and you try to find it using your table. And this attack step is very, very quick. Now, we're not talking about hash functions here, we're talking about stream ciphers. So a standard equation for a stream cipher, you have a key k, an initialization vector iv. You use a function of those on those, and they produce a key stream. You XOR the key stream with the plain text, and you get the ciphertext. There are numerous ways to turn that into a one-way function. One possible way is, okay, let's imagine that we have sort of a constant iv, a magical iv that I call CST here. And if we have this magical iv, we can create a one-way function. We just take hash of x, and we just compute the key stream with x as the key and our constant iv. So we have two conditions to be able to do that. First, we need to find the value of this iv. And second, we need to know enough bits of the plain text to actually recover the key stream and then look up the key stream inside our table. So I won't talk much about GSM. The details are in the paper because I don't have time. I rather focus on GPRS. So this is the GPRS encryption. It doesn't really matter the exact GA algorithm you're using. It's always the same interface. GA takes the session key KC and a value input and a bit D, and input and D forms the initialization vector of GPRS encryption. D is just a direction bit, so it's 0 for uplink and 1 for downlink. And input is in fact where the IV comes from. So the value of input, it's this sort of weird formula. So we have I of UI XOR with something plus something else, modulo 2 power 32, and we have input. Well, in fact, the LFN plus OC is just a frame counter. So it's something that starts at 0, 1, 2, 3, etc. The SX is just a constant. And so the value of input completely depends on the value of I of UI. Now, it turns out in the specification that I of UI is initialized with 0, and it may be changed by the core network. Now, what happens if it's initialized with 0, but it's not changed by the network? Well, you have a mobile that comes to a GPRS network, starts encryption, and the first IV that will be used is a 0 XOR a constant plus 0, and so you have your IV, and another mobile comes and also starts a session and also use the same IV to encrypt the same message or a different message. And so basically, if I of UI is never changed, all new GPRS sessions will use the same sequences of IVs to encrypt their messages. So we have found our magical IV, we have our condition 1. Now we need 128 bits of plaintext. So let's look at what's encrypted. So sorry about that. This is the initiation of a GPRS session. Basically, the mobile comes, it attaches to the network, it identifies itself, the network authenticates the mobiles. Then we have encryption that is enabled. So everything that is below is encrypted messages. And so attachment is complete. And then the mobile asks for an IP address. It activates a PDP context. And once the mobile has an IP address, it sends IP frames encapsulated in yet another protocol that is called SNDCP, Subnetwork Data Convergence Protocol. About what's encrypted in those messages, because we need the plaintext bit that will allow us to retrieve the key stream. So we need to know exactly which bits of the messages are encrypted. Well, we have the LAWA layers, so RLC layer, LLC layer, those are in clear text. And then we have for the GMM protocol, so the signaling messages, the application layer GMM is encrypted, and for the data messages, the SNDCP and everything that's inside is encrypted. If we're looking for non-plaintext bits inside, for the signaling messages, we can find plaintext bits, but those messages are variable. They contain optional elements. It's quite difficult to reliably get non-plaintext or non-positions from them. So instead, we look at data messages. And SNTCP messages, in fact, there is an SNTCP header that is always 32 bits long. And we experimentally verify that it was always predictable, and so it's always known. So SNTCP headers make for a very reliable source of plaintext. So now we are able to define a function to invert. We imagine that we're an attacker. We take the 4 first frames. We know the SNTCP headers of those frames, so we are able to retrieve 128 bits of keystream. And so we're just able to compute a function of that using those magical IVs. So basically, we make this assumption that IOV-UI is 0. We call that a misconfigured network. And if the network is misconfigured, all new GPRS sessions can be attacked. Now, if the network is well configured, meaning that IOV-UI is random and changed each time, then a passive attacker only has a negligible probability of actually finding the correct IV. And so this makes the attack completely impractical. There is still an active attack because we can reset the IV that will be used by a mobile. It's in the proceedings, but I won't mention it further here. So we tested, we ran a few tests. Basically, we set up a 2G network. We used open source implementations, commercial implementations, professional implementations. We used development SIM cards, and we instrumented everything. So we instrumented the mobile, the core network. We performed some network sniffing. We performed some radio sniffing. We decoded GPRS messages. And I will just mention 2 tests. Do SNTCP headers vary? So we say we find that they do not, is because we have tested all those implementations. You have different brands of smartphones. You have different brands of basebands inside those smartphones. And in all those cases, the SNTCP headers were the same. So we conclude that they do not change. And perhaps more importantly, about IOV-UI. So we took a GPRS development board, FC-3B. We implemented a custom firmware for it. And we verified some SGSN implementations. We identified 3 behaviors. The first, IOV-UI is not renewed. Well, this implementation is vulnerable. Second behavior, IOV-UI is renewed to a random value. Good, this implementation is not vulnerable. And third, strange case, but it happened. An implementation sends a new IOV-UI, but in fact, the value is complete, all zeros. So it sends a new IOV-UI and just sets it to its default value. So this implementation is vulnerable. So yes, there exists vulnerable SGSN implementations. Just one slide about GSM. So GSM is a completely different protocol. It's an entire beast. It's another beast entirely. But basically, we're still able to find those magical IVs that allow us to define a function to invert. And for those IVs, we have a very high probability of getting the correct plaintext. And so the probability to successfully attack a GSM session is directly proportional to the session length. GSM is being used to transmit calls, so basically it's proportional to the call length. And now we'll end up with a few numbers. So the time error trade-offs that are studied here are rainbow tables. And so the parameters that we are studying is the pre-computation complexity, the memory that is required, the complexity of the attack step. So how much time does it take to try to decrypt a session, the success probability, of course, and the number of tables. So we ran some benchmarks. So we considered that the pre-computation is done using GPUs. We considered that the attack step is done using some servers, maybe different servers. And so we benchmark different CPUs implementation and optimize using assembly instructions. And we verified that using SSD for storing a large rainbow table did not incur significant performances loss. And so basically, so this, we had to take one table. So this is this one, but you have the formulas in the paper and you have other tables in the paper. So basically, the last line says that if we assume that the pre-computation uses 2,400 GPUs, then it takes a bit less than a year to compute the tables. And if we assume that the attack step requires 10 tables and 10 servers, then it takes 200 terabytes of storage. And if we talk about the probability that we are able to decrypt a GPRS session in a misconfigured network, so to have 75% chance of decrypting the session, it takes 14 minutes with our proposed implementation. So it's extremely fast for an extremely high success rate. And if we take just the data point of 30 minutes GSM calls, we have 11% chances to correctly decrypt the GSM call in 14 minutes. And those results apply to all the ciphers that use a 64-bit key, so A51, A52, A53, GA1, GA2, GA3. We did a responsible disclosure to GSMA, so the standardization body that is responsible for the security of 2G. They acknowledged all the results. They will clarify the role of IOV-UI in the specification. The implementation of A54 and GA4 that use 128-bit key will be made mandatory in mobiles. And they have communicated with worldwide operators and equipment manufacturers to actually verify their network configuration and the implementation of equipments. On the mitigation side, unfortunately on GSM, there is not much you can do. You can enable padding randomization, but basically just half the probability of success. So from 11%, we go to 5.5%. So it doesn't solve the problem. And in GPRS, of course, you need to renew IOV-UI in your network. To make it more difficult to conduct the attack, you can enable frequency hopping. It doesn't make it impossible, but it makes it harder to reconstruct the session. And as a user, you can disable 2G in your mobile phone, but really 2G networks should be phased out, and that's it. Thanks for your attention, and I'm happy to take questions.
Thank you very much. Any questions for Tristan? Niels.
Yeah, hi. Very interesting. Is it correct that you could use this to decrypt the data I recorded 10 years ago?
Yes.
Ah, thanks.
So you said that, I mean, essentially it doesn't matter which cipher you use as long as it's only 64-bit key.
Yeah.
What would happen? I mean, for GA4, you have 128 key, right?
Yeah.
Like if you apply the same technique, I guess the attack is not practical anymore, but like what would the complexity be?
Basically, the precomputation complexity is a bit more than the cost of an exhaustive search. So for 64 bits, you can do that. For 128, that's impossible.
Is there an indication how many mobile operators don't randomize the IV? Which fraction, or?
I have no idea.
So you also mentioned on your last slide as countermeasure frequency hopping, but
Yes.
I seem to remember that some people then hacked the firmware of a phone that does frequency hopping to undo this. So is this still applicable then against frequency hopping, or does it stop the attack?
Frequency hopping does not stop the attack. It just makes it harder for an attacker to correctly reconstruct the complete session and the complete sequence of encrypted messages, because you have to either guess or retrieve the frequency hopping sequence.
But phones can do this, right? I mean, these hacked phones.
I think it's possible, but I don't know of any study that have publicly done that. But yeah, my guess is that it would be possible.
Okay, if there are no more questions, thanks, Tristan, again. Thank you very much. That concludes the session. There is now lunch in the Ligera Commons, and we start again at 2 p.m.